Another object that will undergo oscillatory motion is a pendulum. Might have made this too long. Okay. A lot longer than I needed to. Let's do this. There. So here's a pendulum. This is technically called a simple pendulum because the mass is all at the end. The string is incredibly light compared to the mass of the actual object, so we would call this a simple pendulum. Basically, in order for an object to undergo oscillatory motion, to just repetitively do the same thing over and over and over again, the forces acting on it need to always be trying to bring it back to its equilibrium position. So in this case, gravity, the force of gravity is always trying to get that mass back down to the bottom in order to try to keep it in equilibrium in that vertical position. Now, off to the side it has potential energy, but that potential energy turns into kinetic as it swings down. When it's at its lowest point, it has kinetic energy, so it keeps going and swings to the other side. So we have conservation of energy all over again. Potential to kinetic, back and forth. Turns out, this motion can be described by a sine or cosine function, just like the mass on the spring could, okay, as it swings back and forth. We could look at just its x position as a function of time. We could look at its y position as a function of time. Or we could even look at the angle that it makes with the vertical as a function of time. Any of them. Turns out we end up with the set equation that describes omega, the angular frequency, as a function of time. Okay, so get a feel for this. This mass, this is a 200 Newton mass, so it's just over 2 kilograms. Sorry, 200 grams. So this is oscillating at a certain rate. And again, just like the mass on the spring, the amplitude here isn't affecting the rate at which it oscillates at. Even if I just barely pulled it to the side so it didn't have a very large amplitude, it would oscillate at the same rate. It would take the same amount of time to swing to your left and back to its original position, regardless of how big the amplitude is. Okay. All that means, if I have a bigger amplitude, but it takes the same amount of time, it just means it moves faster. The velocity of it is bigger. If I change the mass, so this one's just over 100 grams, sorry. So I've halved the mass. I've cut the mass in half, basically. But the frequency is the same. The rate at which it's oscillating at is not changed. Okay. If you think about the conservation of energy equations, potential versus kinetic energy, we're talking gravitational potential energy, mgy, versus kinetic energy, 1/2 mv squared, the m is going to cancel. Mass doesn't affect the rate at which it oscillates at. Okay, so it doesn't matter if I have a really small mass or a big mass, unless, of course, drag becomes a factor. As long as drag's not a factor, the mass doesn't matter. What does matter is the length of the pendulum. How long the string is. If I shorten the string, then the frequency is now a little bit bigger. It's swinging faster. There is one other quantity that affects it, but I unfortunately do not have the ability to change it to show you, and that's the acceleration of gravity. If we could take a field trip to the moon, this would oscillate at a different rate than it is right now. So same length, same mass on the moon would be different. Turns out the equation for omega is the square root of g, 9.8 meters per second squared here on Earth, over L. L is the distance from the pivot point at the top down to the center of mass of our object. So it's how long it ends up being. And likewise, since period is 2 pi over omega, period for a simple pendulum will be 2 pi times the square root of L over g.
So, center of mass, do you have to use pi? No, I guess
Not if all the mass is located at the end. If you have basically a point mass there, then you're good. You can just use the, basically from here to the middle of here, and you're good to go. If you're looking at something like a grandfather clock, where you have the big beams all the way down to a big ball, then moment of inertia would be important. The equation is slightly different in a case like that.
Are we going to touch examples like that with grandfather clocks and whatnot?
No.